Let's take a few minutes and look at the practice questions about two-sample inference. So in this question, we're comparing the average number of units that are assembled for two new techniques. So I already know we have random assignment to one of the two techniques. So that means I have two groups and I'm comparing means in this context. So this has to be then a two-sample t-test, and this is an experiment because we are randomly assigning to the two different techniques. So those would be our two treatments. So in question number 2, the key is that we have all of the ages of the American presidents, and we also have all of the ages of the British prime ministers. So something to think about. This question says that we want to create a 95% confidence interval for the difference in mean age at the time of election to office. But we have a census. We know all of the ages of the American presidents and all of the ages of the British prime ministers. So the reason that this procedure isn't appropriate is because the entire population's measured in both cases. So you can actually calculate the actual difference in the means. You don't need a confidence interval to try to capture the true difference between those means. Find the mean for the American presidents, find the mean for the British prime ministers, subtract them, you'll know the truth, and be done. No need for a confidence interval. For some reason, the most commonly chosen wrong answer was this question here, where people said the ages at the time of election to office are likely skewed rather than bell-shaped, so the assumptions for using this interval formula are not valid. So I'm not sure necessarily why you would believe that they are skewed. We've actually looked at the ages of the American presidents at inauguration, and the truth is they're relatively bell-shaped. We actually can approximately use the normal distribution to represent them. So the problem here isn't about the assumptions. The problem here is we can calculate the true difference, so there's no need to build a confidence interval. So question number 3. So the first thing to consider, you're building a confidence interval here, and you know the level of confidence. So if you look at the work, understand we have the statistic, and then we are adding and subtracting. This is the margin of error, which is made up of the critical value times the standard error of the statistic. So the first thing you can do is just go through and look for which questions have the correct critical value. So this is about capturing the difference between two population proportions. So this is about z-scores. I know for 90% confidence, the z-score for 90% confidence is the 1.645. I know the 1.96, those are for 95% confidence, so I can already eliminate those two answer choices. So then, really the rest of the question, if you compare the formulas, there's no difference in the statistic. It's 50% minus 30% for both of, for all three of the answers that remain. So that 50% is the proportion of non-luxury cars with bumper stickers, 125 out of 250. So the other proportion is for luxury cars, 30 out of 100. So the bottom line, if you use your formula sheet, you can determine which of the formulas for the standard errors is the correct formula, and it's actually this one right here. So for the standard error, this is for the non-luxury cars. We have observed in the sample data 50% do and don't have bumper stickers out of that sample size of 250. For the luxury cars, it's 30% do and 70% don't have bumper stickers out of 100. This is the correct formula because we're using the correct formula for the standard error. Comes straight from the AP formula sheet. So in this question here, we're interested in comparing the levels of physical fitness for students attending nearby community colleges and those attending four-year colleges in the town. So we have a random sample of 320 students from the community college. We have the mean and the standard deviation from that college. That is their fitness scores. We also have a random sample of 320 students from this four-year college, and we also have their mean and standard deviation for their fitness scores, but we don't really need to use those because a two-sided t-test has already been run, and I know the t-score. So understand, I know that if we were working with a normal distribution, we're working with the t-distribution here, but if we were working with the normal distribution, almost all of the data is captured within 3 standard deviations of the mean between z-scores of positive and -3. So because our sample sizes are 320 here, because they're so large, t-scores and z-scores from the normal distribution will look very similar. So I know there is very, very little area left to the left of or below a t-score of -3.27 or to the right of a t-score of positive 3.27. So I know the p-value here is very, very low. So because of that, I can choose this option. I don't even need to calculate the p-value. I know that it's less than 5%. So I know that mean fitness scores for these two groups are going to be significantly different. And the question is, we are looking for comparing, we're looking for evidence of a difference in physical fitness between these two groups. So for question number 5, important, the computer output shows the results of this test, and this is the mean weights for a random selection of baseball players. This is the mean weights for a random sample of hockey players, so these are college athletes. The null hypothesis then is always an equation. Notice the alternative is this, where we're looking for evidence that the mean weight for baseball players is less than the mean weight for hockey players. So notice I have box plots here. I have the sample sizes, the means, the standard deviations. We're even given the standard errors. Here is the 95% confidence interval for the difference between baseball players and hockey players. But notice then here is the t-test for a null hypothesis. Of course, the null hypothesis is that their means are equal. The alternative is a less than alternative as suggested in the question. And notice that we should really ignore the confidence interval here. Clearly, we are interested in the results of the test because all of the answers are giving us a level of significance. So we're looking at the test, not the confidence interval. So understand, the first answer is wrong. The mean weight of baseball players is not significantly lower than the mean weight of hockey players at the 10% level. Well, if that's our level of significance, it is significantly lower because our p-value is less than 10%. So here we go. This is the correct answer. The mean weight of baseball players is not significantly lower than the mean weight of hockey players at the 5% level. If you change the level of significance to 5%, now you can say it's not significantly lower because our p-value is not less than 5%. It's greater than 5%. It's about 7.6%. So the problem with this answer, which was relatively commonly chosen by students, we're not looking for evidence of a difference. We're looking for evidence of a less than alternative, where the mean for baseball players is less than the mean for hockey players. Here, we're not looking for evidence of higher for baseball players. We're looking for evidence of a lower mean weight for baseball players. That's why that one's wrong. This one was also relatively commonly chosen by students. So here, this says the mean weight of baseball players is significantly lower than the mean weight of hockey players at the 5% level. That's not true. That would be a true statement at the 10% level, but at the 5% level, it's not. The null hypothesis won't be rejected at the 5% level because the p-value is larger than 5%. So for question number 6, we're looking at 2 brands of batteries, and we're interested in which one lasts longer. So we have 2 samples worth of data, we have a direction, and we're looking at quantitative data here. So these are the hours of battery life shown in the table below. So provided the assumptions for inference are met, which of the following tests should be conducted to determine if brand A batteries do in fact last longer than brand B batteries? Well, guys, it's not a two-sided alternative because we are given a direction. We're interested in a longer alternative we're interested in if brand A does in fact last longer than brand B. So this has to be a one-sided test. So there are 2 samples worth of data because there are 2 brands of batteries, and because this is quantitative data, we're going to have to work with means. So this question is about a t-test. So question number 7, I'm going to read this whole question. So if an experimenter conducted a 2-tailed test on a set of data and got a p-value of 0.44, fine. If the experimenter had conducted a 1-tailed test instead on that same set of data, what's true about the possible p-values the experimenter could have obtained? So let's look at a picture here. So in a 2-tailed hypothesis test, or a 2-sided hypothesis test, in this case, the test statistic either has to be a negative value or a positive value. Let's assume that it's this negative value here. So understand that if this is the test statistic, the likelihood of a statistic as or more extreme could be lower than that test statistic on the negative side, or it could be higher than the absolute value of that test statistic on the positive side. So look, the p-value would come from adding these 2 probabilities together. That's where the 44% came from. But that's on a 2-tailed or a 2-sided test. If your alternative hypothesis was a less than alternative, notice then we would only be interested in this value here being less than our test statistic. So the p-value would be 0.22. But don't be fooled. If this is our test statistic, the alternative hypothesis could also be a greater than alternative. So the p-value could also be the area at the test statistic or above. So understand that would be 1 minus this 22%. That would be 78%. So there are 2 possible p-values. It could be either 22% or 78%. The most commonly chosen wrong answers were these 2. And at some level, if you chose the only possible p-value to be 0.22, you're not wrong in that the 0.22 is a bad choice. The 0.22 is half of the 0.44. That's a good choice. The problem is it's not the only possible p-value, because that's the p-value for a less than alternative. It could also be a greater than alternative if the test statistic is on the negative side. So here, these people just subtracted incorrectly. So 22% from 100%, that's not 88%, it's 78%. So that very first answer there, which was commonly chosen as a wrong answer, that's just an arithmetic mistake. So for question number 8, so this is a randomized experiment here. So we're trying to figure out which of the fertilizers give the best yield of tomatoes, which produces the most tomatoes. So a total of 33 tomato plants were grown. 16 used fertilizer A. These are those results. 17 used fertilizer B. Those are those results. So the distributions didn't show any skewness and there weren't any outliers. So I know that the conditions are at least met to complete inference here. So which of the following statements best describes the conclusion that can be drawn from this experiment? So remember, the null hypothesis is that the yield is going to be the same between fertilizers A and B. Bottom line is you're looking for a difference. So this is going to be a 2-sided alternative. So if you use the 2-sample t-test, again, it's a randomized comparative experiment where random assignment is creating 2 groups. So I need to use the 2-sample situation. So I know it's a t-test because I'm working with means. It says average, but it's quantitative data. And I know that it's a 2-sided alternative because I'm looking for evidence of a difference. So if you use the 2-sample t-test, so here's the data for A, here's the data for B, so you need to put in the sample mean, the sample standard deviation, and the sample size for both of those groups. This is the p-value that you should get. So then you can go through and you can determine which of these answers actually captures this p-value here. That's what we're interested in describing. So it's down here. So our p-value of 0.016 or 1.6% is captured between the 1% and the 5%. So there is evidence of a statistically significant difference in yields between fertilizer A and fertilizer B. We have a relatively small p-value. The idea here is with this p-value that's less than 5%, we would reject the null hypothesis. So we do have evidence of a difference in yield on average between fertilizer A and fertilizer B. That's what we mean by a statistically significant result. In a significant result, we're rejecting the null hypothesis. So in this question, we are assuming that between these two drugs, that the drug has no effect. So there's no difference between the effectiveness of the drug and the effectiveness of the placebo. So understand, what we are looking at here, though, is a large number of randomized experiments were conducted. So we're looking not at large samples, we're literally looking at a large set of experiments that have been used to determine whether taking a particular drug would decrease the chance of getting a certain disease. So we're looking at comparing the chance of getting a disease between using the drug and using a placebo. So that's going to be about proportions. So for each of the experiments, the drug effect is the difference between the proportion of people taking the drug who got the disease and the proportion of people taking the placebo who got the disease. So those proportions will be the same if the drug has no effect whatsoever. And we're assuming that that's the case. We're assuming essentially that the null hypothesis is true. And then in all of these experiments, the truth that we were hoping to detect was that there's no difference between the drug treatment and the placebo treatment. So what would we anticipate? So which of these options, 1, 2, or 3, so of them, which of them would be true if we're looking at the results of a number of experiments? And it's important to believe the null hypothesis is true. So it's important to interpret 1, 2, and 3 under the assumption the null hypothesis really is true. So number 1, p-values will be greater than 5% for about 95% of the experiments. That's a true statement because understand the p-values will be less than 5%, about 5% of the time, just by random chance alone when the null hypothesis is true. And when that's the case, those are experiments where type 1 errors are committed. So for those 5% of experiments where they have low p-values just by random chance alone. Again, the null hypothesis is true, but if you do something using enough experiments, eventually you'll get a small p-value just by random chance alone, even though the null hypothesis is true. So in question number, or rather not question, but in statement 2, there will be about an equal number of experiments showing positive and negative values of the drug effect. That's a true statement because the truth is 0, but by random chance alone, sometimes you'll be above 0, sometimes you will be below 0. And if the conditions are met here for inference, we would expect about an equal number to get positive or negative test statistics. So because 0 should be in the middle, because 0 is the truth. So number 3, when 95% confidence intervals for the population drug effect are constructed, these confidence intervals should include 0 about 95% of the time. Well, that's a true statement because remember, we're building confidence intervals using a method that should capture the truth about 95% of the time. Well, we have many experiments. So what that means is about 95% of those experiments should be capturing the truth, and the truth is 0. So that should actually be captured within the confidence interval. So if 0 is actually captured within that confidence interval, you are failing to reject the null hypothesis. You're not rejecting the null hypothesis. So the truth is all of these are true statements. So the correct answer is 1, 2, and 3. Those are all true. I actually think number 9 is a pretty tricky question because you're not considering just one experiment, you're considering the outcomes of many, many experiments, and you have to read carefully enough to realize that you're supposed to believe that in all of the experiments, the null hypothesis was actually true. So question number 10, a physician believes that the exercise habits of East Coast adults are different from the exercise habits of West Coast adults. So she gathers information on the number of hours of exercise per week from a random sample from the East Coast and the West Coast. So which of the following would be an appropriate null hypothesis for this study? So understand we are collecting quantitative data, hours of exercise, and it's a 2-sample situation. situation. But remember, what we're interested in is an appropriate null hypothesis. So a null hypothesis is always an equation. We're assuming that there is, if you will, no difference. We are looking for evidence of a difference between East and West Coast habits. That means that the null hypothesis would believe that we don't believe. The null hypothesis would be that we don't believe there's a difference between, in this case, the hours of exercise on average between East and West Coast adults. Again, it's a two-sample situation. It's quantitative data, so we have to be looking at means. We have to be talking about averages. So this can't be the correct answer, the first one. The average number of hours of exercise per week for East Coast adults, at least it's about averages, that's good. But we're not looking, the null hypothesis is not about a less than alternative. The null hypothesis should be about an equation. That's why the second answer is the correct one. So the average number of hours of exercise per week for East Coast adults, so that would be mu for the East Coast, the truth from the East Coast, is the same as the average number of hours of exercise per week from the West Coast. That would be mu for West Coast, that mu being the true hours of exercise per week. So looking at some of the other answers then, look, the null hypothesis is about an equation. The null hypothesis would not say that the average for the East Coast is different from the average from the West Coast. And remember, this is about quantitative data. So the null hypothesis is about the two means being the same. It's not about a probability. So, and last, again, the null hypothesis is an equation. It should not have a direction. The average number of hours of exercise per week for East Coast adults is greater than the average number of hours of exercise per week for West Coast adults. Again, this is not about an alternative hypothesis which could have a direction. The alternative hypothesis in a test can be a less than alternative, a greater than, or a not equal to alternative. Actually, in this case, because we're looking for evidence of a difference, that the alternative hypothesis would be a not equal to alternative. But this question is about the null hypothesis. That's always an equation, not greater than. It should be the second answer because we believe in the second answer that the mean is the same for both the East Coast and the West Coast. That's what the null hypothesis states.